Hi everyone, my name is Leila Balkhi and I am the project manager for the Integrated Modeling Program for Canada, or IMPC in short. IMPC is one of the projects under the Global Water Futures Program. It's based out of the University of Saskatchewan's Global Institute of Water Security. I'd love to tell you a little bit more about the project, but today I in fact have a special guest, our principal investigator of the project himself, who's here to tell you a little bit more about what we do here at IMPC. Please join me in welcoming Dr. Salman Rizavi.
Thank you, Leila, for that kind introduction. Hello, everyone. My name is Salman Rizavi. I'm an associate professor at the School of Environment and Sustainability, University of Saskatchewan. I'm also a core member of Global Institute for Water Security. So we thought we would take this opportunity to welcome you to the 5th annual meeting of IMPC that we typically run about this time of the year, and give you some brief update of what has been going on in the past couple of years. And we chose this time to create a video in advance so you could watch it at your own convenience and just be prepared for the follow-up events that are going to run next week. So stay tuned, and at the end of this talk, we will walk you through the events that are going to happen next week and the week after. So I'm going to take this opportunity now and give you a brief overview of what I have been doing in collaboration of many colleagues, and in particular, the pieces done by HQP that have been directly working under my supervision and some co-supervised by some of other colleagues under IMPC. Okay, so I think in the next 20 minutes or so, I'm going to give you some updates on integrated modeling, sensitivity analysis efforts, and machine learning. And machine learning has been something fairly new, and we'll get to that, and basically our developments in the past year or so, and some of our future vision on how we're going to proceed with that. So IMPC in general has been a largely collaborative effort. From the research perspective, we've been closely working with the core modeling team of Global Water Futures, and there has been a lot of interactions and support. And some of the pieces that are presented today as well have been partly supported by the core modeling team. And of course, so many colleagues in the Global Institute for Water Security. We've been also working with many collaborators, partners, industry partners, government partners, and some of them have been listed on this slide. And this is our interdisciplinary team. A number of us as co-investigators have been working together, and we're coming from different backgrounds: engineering or hydrology, ecology, social sciences, computer sciences, atmospheric science, economics, and geography. And different people in 4 universities have contributed to basically make IMPC and GWF happen in general in the past several years. So let's just refresh our minds about the overall hope and vision that brought us together in the first place, and that was all around one word: integration. And the idea has been to bring the worldviews and models of different disciplines: climate models, hydrology models, water resources systems models, economic models, socio-hydrological models, as well as the indigenous knowledge, all together. And we've been trying to be as inclusive as possible in the integration, given the constraints and technical constraints and semantic constraints. And we've been working significantly to basically bridge the different fields and basically break through disciplinary barriers to bring and somehow couple these models together. So in the next slides, I'm going to just showcase some of our efforts under each of these. Of course, I'm not going to be covering everything. And you're going to hear a lot more in the follow-up events during this 5th annual IMPC meeting next week. So I'm just going to give a quick overview and showcase some, but just stay tuned for the rest. So what I would like to begin with is our efforts on hydrologic modeling, primarily focused in the past couple of years on permafrost thaw and permafrost thaw modeling. And the reason that we've been really looking at this significantly is that under global warming, we know that our permafrost dynamics, temperature dynamics in particular, have been changing and are projected to change significantly in the years to come. And from hydrologic point of view and infrastructure point of view, we are concerned with the active layer thickness, and basically that the top few meters of soil, or sometimes even less than a meter, that become active in summertime, basically depending on the temperature profile and the weather of that year. And of course, there are evidence that this active layer thickness is expanding further and further to the ground, and that will have a lot of implications. Of course, immediate ones are more methane emissions to the atmosphere, which will provide positive feedback to warming. And on top of that, it has implications for soil compaction, land subsidence, and as a result, for infrastructure. And where I'm coming from, hydrology, it also can change some hydrologic regime on the land surface. So it can change the lateral connectivity of the soil in those topsoil layers. And it's quite important to capture those permafrost dynamics properly and represent them in the models. So we've made some progress in terms of modeling. Of course, one major limitation up in the north is data, but models can be seen as explorative tools here to help us identify possible trajectories of permafrost evolution in the future, of course, constrained by the data available, but that helps us understand what might happen in the future. And this is Mohammed Abdulhamid, our man in IMPC working on permafrost modeling, and he's been basically pushing this work forward. He's already published or has in review a couple of papers, and basically this is the man behind all these permafrost efforts in the past year or so. Let's move to water resources systems modeling. Now we have a system-wide water management model for the entire Saskatchewan River Basin. So this is a fairly complex system with a fairly complex model now, simulating more than 50 reservoirs, so many irrigation nodes, different interests, transboundary water agreement, priorities, and so on. And everything is now embedded inside this model, and it can help us simulate the entire water management system coupled with the hydrologic system and basically the Rockies as our source, as our headwaters. And it can help us assess different trade-offs between a range of stakeholder interests, such as irrigation, hydropower, environmental flows, cultural flows, indigenous needs, and so on. And Mustaqim Ali Shah has been our man working on this and pushing this forward with the help from other folks like Kasra Keshavarz, Nudo, and others. And Mustaqim has now moved on to a new role in Alberta Environments and Parks. We've been also trying to bridge local scale water resource operations, like the operation of a reservoir or water allocation, to river basin economy. And let me explain to you why that is important. So this has been a primary focus of integration for us in the past couple of years. And the reason that is important is in traditional engineering approaches to hydroeconomic modeling, and basically the kind of school that I'm coming from, we typically only look at direct water using sectors, like hydropower, like irrigation, and basically any sector that directly takes water and produce or contribute to the GDP. But this is only a small fraction of the whole economy. On this plot, on the pie chart, you're looking at the contribution of economic sectors to GDP of Alberta and Saskatchewan. And only around 30% of economic sectors directly use water. So the rest of the economic sector is also connected to water, but indirectly by their connection to these water using sectors. But often, or perhaps almost always, in engineering approach, we ignore those intersectoral interactions that can be quite important. And basically, we saw the need to bring the full economy to water resources modeling and account for all intersectoral and interregional interactions. And we did so, we accomplished this by integrating macroeconomic models like input-output models to water resources systems models. And to give you just some results, for example, by this integrated modeling platform, we've been able to assess the impact of the recent $4 billion investment project announced in Saskatchewan. And the estimates based on these models show that how this $4 billion investment might contribute to the economy of different regions across the Saskatchewan River Basin. For example, based on the prices of year 2015, we can see that that $4 billion investment would contribute somewhere around $170 million to irrigated crop and animal production in south of Saskatchewan, which makes a lot of sense, but it can also contribute to other sectors. For example, about $1 million in a year to information and cultural industries. That is not a water using sector, but it will benefit from intersectoral and interregional interactions. And more importantly, let's look at upstream in Alberta. So Alberta will also benefit economically from this project. For example, $29 million to manufacturing in Alberta will be the added value of these investments in Saskatchewan and also to the other sectors. So basically, this type of integrated modeling can help us more to understand when water can move uphill and water doesn't only flow downhill, and the impacts of some policy interventions or water allocation investments can go way upstream. And this means what we're talking about is a basin-wide problem and basically needs to bring different stakeholders from across the basin together. And a Saskatchewan problem is not only a Saskatchewan problem, it should really elevate the conversation for every other stakeholder involved. So this is the lady behind all these integration efforts of bringing economy and water resources management together, Leila Eamon. And you can see some of her papers recently published on this. She finished her PhD last year under myself and Professor Roy Brower at the University of Waterloo. And since then, she has joined the core modeling group of Global Water Futures. Moving on to the next piece, socio-hydrologic modeling, and why that is important, because we need to look at the demand management as well. Not everything is about water supply. The demand side is also quite important. Either you want to manage it, or you want to have a good handle of how the water demand might change in the future. So for this piece, we looked in particular, we looked at the rebound phenomenon or J1's products in water demand. And we did so by the help of agent-based modeling. And our area of focus was in the agricultural irrigation communities in Alberta. And basically, to just briefly say what rebound phenomenon is, so typically when we come up with new water policy, for example, to incentivize high efficiency irrigation, we can, by doing that, we can reduce the water use in the short term, because when you convert your irrigation practice to something more efficient, you of course use less water. But history has shown in many different parts of the world that yes, that's true, but after some time, this reduction in water demand can rebound, because then there is more water and there might be other incentives to expand irrigation in some other way. And basically by doing so, you might see after some years that you are even using more water, and there is more demand for water. So these might be sometimes unintended consequence of a policy, and it's very important to have an understanding of. And to do so, we developed the agent-based models as explorative tools. And of course, these models are very stochastic, typically cannot be very predictive. We use them as explorative tools to come up with different possible plausible scenarios of what might happen in the future, to give us an understanding what might be the unintended consequences of some policy change. And this is the man behind this work, Mohammad Qureshi. And on the screen, you see a couple of his recent papers published on this topic. And he also finished his PhD recently, and he's currently also working under core modeling for a limited time. And then he's been offered a very good postdoc position somewhere. Okay, I'm now shifting gears towards another part of IMPC, which is around sensitivity analysis and uncertainty analysis, and methods that we've been developing over the past few years to support our modeling efforts in IMPC and beyond, and even beyond hydrology, because sensitivity analysis is model independent. It can be used wherever you deal with models, even in aerospace industries or finance, or basically wherever you deal with models. So we had this fairly big undertaking in the past couple of years. Basically, a group of scientists came together back in late 2019 in Barcelona. It was just a few months before the pandemic hit, to basically ponder about the future of sensitivity analysis. And sensitivity analysis is a relatively young discipline, or a meta-discipline, because it brings different disciplines together. And back then, we pondered about, okay, how far we have come. Can we now call this a discipline that has come of age? And the answer in general sentiment was yes. And okay, if this is now a discipline that is mature enough, how the future of it might look like. So during this event, we basically came up with some possible future avenues of how the sensitivity analysis efforts might roll out, not only in hydrology, also in other fields. And you can see the outcomes of these efforts on the screen, the papers. And there has been a lot of follow-up conversation on how these can feed into different areas of science. And on this, sensitivity analysis, some of you might already know that we've been working in the past 7 years or so on our in-house sensitivity and uncertainty analysis toolbox based on variogram analysis of response surfaces, or VARS. And there has been in particular significant progress in the last year. What you're looking at is the VARS-TOOL.com or VARS-TOOL.com VARS website. Now on the top, you can see a new tab, download the Python package. We previously had everything in MATLAB. Now we have also everything in Python, with a lot of new features that we didn't have in MATLAB. So we've really expanded significantly in this area, and we've already created some educational videos, and more are forthcoming. And big thanks to Kasra Keshavars and Corder Blanchard, who've been doing this phenomenal job in the past year or a couple of years to get us here. And now, for example, if you go on GitHub or on that web page, you can go directly to our GitHub page where you can find how to download this package, multiple tutorials, what kind of research questions you can answer with these tools, and so on. And I expect in the next year or so, we're going to see way more on this. And so Cordell is still working on this. And yeah, just stay tuned for our future videos and updates on what you can do with VARS-TOOL beyond what you might have been already doing. Okay, I'm now again switching gears towards machine learning. And this is an area that I have personally revitalized interest in. So in my former life, I was a machine learning AI person for some years in early 2000s. Then for some reasons, I abandoned the field. But in the past few years, basically, I got back to it after all the tremendous progress that has been made recently in different fields, in particular image recognition and natural language processing. And of course, we all benefit from AI now on a daily basis through our smartphones and so on. So we've started some initiative looking at recent machine learning progress in earth and environmental sciences and beyond. And of course, we can have a look at the two papers shown on the screen. But in this effort, and basically this involved a number of scientists, both from process-based modeling background in hydrology and earth sciences, and also those from more machine learning, data-driven type backgrounds. And we've been talking and working together. And basically this picture shows how our perspective of how far we have come, where we used to be, where we are now, and where we might go in the future. And basically there was some discontent that there has been an isolation phase that persists almost to date. And basically machine learning techniques and process-based modeling techniques have been evolving in isolation with limited interactions. And of course, in the past 10 years or so, there has been some efforts on hybridization to bring the two worlds together. But the argument is these hybridization efforts have been mostly still rooted in isolation. And a lot of it, of course, depends on the modeling purpose as well, whether or not you want to use your model for nowcasting and prediction, scenario analysis, or diagnostic learning. And for different purposes, you might want to do your modeling work differently, or to hybridize the two worlds differently. Anyways, the perspective or the argument for the future is that we need to have perhaps a co-evolution phase where machine learning or computer scientists and earth and environmental scientists should work together in a very interdisciplinary environment to basically try to reconcile their worldviews towards problem solving. And anyways, for more, you may refer to these papers, but we've started some recent research. And Kaylon Lee has joined us group recently working on this. Unfortunately, I don't have his image shown here, but stay tuned in the next couple of years for some progress in that area as well. International collaborations. So we've been fairly active to collaborate internationally, primarily with the UK and Australia, and a lot of it was as a result of my sabbatical plans that happened last year. And of course, many visits got canceled because of the pandemic, but we managed to do quite a bit of work internationally. What I want to showcase here, though, is our work with a large group of scientists from different countries on global flood and drought risk analysis under a paired event approach. And by paired events, what we mean is two, for example, flooding events that happened in relatively close proximity in time, and basically in the same region, and see what we've learned from the first event and how we have basically reorganized or adapted to those type of floods, and how we performed in the follow-up event that happened some years down the road. And this piece was under the framework of IASH, International Association of Hydrological Sciences, and has concluded recently, and there is going to be a paper coming out soon. Stay tuned for that. And in this work, our contribution, our Canadian contribution, was to contribute to case studies, one for the Assiniboine River floods and the other one for Ottawa floods. And basically we assessed the role of policy and governance and science in those flooding events and what we've learned and where we might have possibly failed or could do better. And the same thing for every other case studies across the world, and lessons learned were quite significant in that area. And these ladies have been the primary contributors to this international collaboration from our side, working with me, Haley Carson and Leila Balkhi. And we've been looking at these floods, collecting data, analyzing both the science side and the policy side, and how we've been doing in relationship to other efforts and case studies in other parts of the world. So there is a paper now under consideration, and at some point it will be out. So stay tuned for the results. And basically, my personal take is that I have learned a lot from this international collaboration and what we can learn from each other in different countries in face of catastrophic events such as flooding and drought, and how can science better inform policy, and basically science and policy can work together in a more effective way. We've been also fairly active around EDI, equity, diversity, inclusion. I just wanted to showcase here two pieces that I have written from my personal perspective as a non-native English speaker and first-generation immigrant to Canada, reflecting on my past experience and what I have learned. Basically, yeah, I'd love to discuss any of these pieces with anyone who might have interest in the future as we all work for a better world. And of course, EDIs are quite important. And the big news, we have a new addition to the IMPC team. Ashley Duffy will be joining us on July 4th. 2022 as our new engagement and policy research analyst. She has a background in freshwater sciences and a master's in environment and sustainability, along with work experience as an environmental consultant, researcher, NGO contractor, First Nations planner, and even a farmer. In the past, she has also worked with the GWF Prairie Water Project and then moved on to work for Water Survey of Canada. So welcome, Ashley, to the team. We are very excited to have you, and we have a lot of plans for the next year having you. So here, Leila, I think I'm returning it back to you for final conclusions and remarks.
Thanks so much for that, Saman. There's definitely a lot that has been done. I know we started with the goal of having this video within the 10 to 15 minute mark, and now we've doubled that. So that just is a testament to the amount of work that has been done. I just wanted to point to this slide and the website link on the top right-hand corner. Please come join us to these events. These are all workshops and presentations that are meant to be very participatory. You're welcome to bring your questions, bring your reflections, bring your comments, and please engage in a lot of discussions for us to help us get better. I'll leave this at this slide, and we hope to see you there in our next week's meetings event. Thank you.
Thank you, Leila. Bye, everyone. Looking forward to seeing you in the workshops.